Welcome, curious minds, to the deep dive. Today, we're going to dive into what might seem like just a pile of numerical puzzles, but they're actually powerful tools waiting to be unlocked.
That's right. We're taking a deep dive into a collection of these Regions Review packets. Think of them as a kind of treasure trove of example problems. They span some really crucial units in advanced algebra and pre-calculus.
And our mission today, well, it's not to solve every single problem step by step.
No, definitely not.
It's more about navigating these mathematical landscapes, extracting the most important nuggets of knowledge, the core concepts.
And the surprising connections sometimes.
Exactly. The things that really make you feel well-informed. Think of it as a guided tour through polynomials, rational exponents, functions, complex numbers.
And the world of exponential and logarithmic functions, too.
We've got several packets here, units 1 through 11, just packed with problems, and importantly, their solutions.
So we'll explore a selection, highlighting some key methods and the underlying principles that make them work.
Okay, let's get into it. We're starting with the fundamental building blocks: polynomials, exponents, and radicals. First up, polynomials. These seem foundational.
They really are. When you're dealing with polynomials, these expressions like 5 by 2 or 2 by 3, 2, the real lesson isn't just about calculating the answer.
Right.
It's more about the discipline, the meticulousness, subtracting them. A problem like 5 by 2, 2 by 3, 2, well, it demands really careful attention to how that negative sign distributes after you square the 2 by 3 part.
Oh, yeah, that's a classic trap. Easy to miss a sign.
So easy. But doing it correctly, working through the expansion and distribution, that gets you 2 by 2 plus 12 by 9. It seems like a small error, but it can have big consequences down the line.
It really is like building with Legos, one piece wrong.
Exactly. And sometimes you need to break down these bigger, more complex polynomials. That's where something like polynomial long division comes in handy.
Right, long division. Seems a bit old-fashioned, maybe.
Maybe, but it's actually a really powerful way to test if one polynomial is a factor of another.
How so?
We'll take dividing, say, 27 by 3 plus 9 by 2, 3 by 10 by 3 by 2. You go through the long division process, and if you end up with a zero remainder...
Which happens here.
Yes. That tells you that 3 by 2 is a factor, and the quotient you get, 9 by 2 plus 9x plus 5, that's your other factor. It's like finding the hidden ingredients.
Okay, so division helps find factors. What other ways are there to factor? It feels like there are a lot of strategies.
You're right. There are. And the packets show a good variety. One common strategy is just recognizing patterns, like breaking down by 4 by 2, 12. You might spot that it looks like a quadratic, sort of, and factor it into by 2, 4 by 2 plus 3.
And by 2, 4 factors further, of course.
Precisely. Difference of squares. Another key pattern is sums or differences of cubes, like y9 plus 27y9. That might look intimidating.
A little bit.
But if you recognize y9 as y33 and 27y9 as 3 by 3, 3, you can use the sum of cubes formula to get y3 plus 3 by 3, y6 3 by 3 by 3 plus 9 by 6.
It's about seeing the underlying structure.
Exactly. It unlocks the problem.
And what if there isn't an obvious pattern? We saw factoring by grouping, too.
Right. For expressions like by 3 plus 5 by 2y plus 5x plus y, it doesn't immediately look factorable. But if you rearrange a group terms, like by 3 plus 5x and 5 by 2y plus y, wait, no, that's not the example. The example is by 3 plus 5 by y plus 5 by 3 plus y. Okay, let's regroup that. By 3 plus 5 by 3 is 6 by 3, and then 5 by 3 plus y. Maybe the example in the notes was slightly different. Let's use the one mentioned. By 3 plus 5 by 5 plus 5 by 3 plus y, if we group by 3 plus 3 plus 5 and 5 by 3 plus 5 by 3.
Yeah.
No, wait, the groupie example was likely meant to be something like by 3 plus 5 by 2 plus x plus 5.
Okay, let's imagine that one. By 3 plus 5 by 2 and x plus 5.
Yeah.
You factor out by 2 from the first group to get I2x plus 5 plus the x plus 5. Now you have common factor.
X plus 5.
Yeah, so you get x plus 5 by 2 plus 1. It's a clever trick for when other methods don't immediately work.
Okay, moving on from polynomials to exponents and radicals, these can look really messy sometimes.
They can, but mastering the rules, especially for rational exponents, is incredibly useful. We looked at an expression like back by 2, 4 by 1, 3.
Whoa. Yeah, it looks complex. But the trick is just applying the exponent rule step by step. Remember, a negative exponent flips the base inside the parenthesis. Then raising a power to a power means you multiply exponents.
So that 4 by 1, 3 becomes...
Well, 4, 3 is 164, and by 1, 3 is by 3. So the denominator becomes by 3, 64.
Okay. So we have by 2 divided by 4e64.
Right, and dividing by a fraction is multiplying by the reciprocal. So it's by 264 by 3.
Which simplifies to 64x. Huh. The packet note says 64 by 9. Let me recheck that exponent rule. 4 by 1, 3. The nominator applies to the 4 on the ice 1, so it's 4 3 times by 1, 3.
Right, 4 3 is 164, and by 1 3 is by 3. So the denominator is 164 by 3, or by 364.
Okay, so the original expression is by 2 divided by 3, 64. That's by 2, 64 by 3, which simplifies to 64x, still getting 64x. Let's reread the packet description. By 2, 4 by 1, 3. Maybe the packet meant by 2, 4 by 1, 3. Let's assume the original transcription by 2, 4 by 1, 3 was correct. We got by 2 by 3, 64 equals 64x. Let's check the packet solution reference, which says 64 by 9. Where could by 9 come from? Maybe the original was x2, 4 by 1, 3. No. How about by 2, 4x, 3? No. Let's stick with the original expression. By 2, 4 by 1, 3 simplifies to 64x. The packet solution might have a typo or refer to a slightly different problem. The process of applying exponent rules is the key takeaway anyway.
Absolutely. The rules are the important part. And using those rules lets you simplify things dramatically.
So how do these rules help solve equations, like the one scored by 312 is Uxuty?
It's pretty elegant, actually. The core idea is get everything to fractional exponents.
Yeah.
Scored by 5 is just by 52.
Okay.
And by 312 is by 32.
Right. Power to a power, multiply.
Exactly. Then, when you divide terms with the same base, you subtract the exponent. So you have x to the power of 52, 32.
Which is 22, or 1.
Right. So the left side simplifies 2 by 1, which means y must equal 1. It's a quick way to find that unknown exponent.
That makes sense. And simplifying complex radicals, like Kubert 37a8, 7b9, Kubert 73b3, what's the strategy?
The principle is to look for perfect cubes inside the cube root. Since you're dividing cube roots, you can actually combine them under one big cube root first.
Oh, right. Divide the inside.
Yeah, so 378.7 is 54, a7a3 is a4, and by 9b3 is b6. So now you have cube root 54, a4, b6.
Okay, and now simplify that.
Now simplify. There's a 4 is 27, 2, and 27 is a perfect cube. 33, a4 is a3a, b6 is b2, 3, so that's a perfect cube.
So you can pull out a 3, an a, and a b2.
Exactly. You pull out the 3, the a, and the d2, what's left inside the cube root?
Okay.
That's the 2, the extra a. So you get 3b2 cube or 2a. It's about breaking it down.
Neat. And rationalizing denominators. Why is that important for something like scort 50 sieve, scort 5 dark rate?
It's mainly about standard form and making it easier to work with later. We generally avoid having radicals in the denominator.
So how do you get rid of it?
You multiply the top and bottom by the conjugate of the denominator. The conjugate of 5 scort 5 is 5 plus scort 5.
Okay, multiply top and bottom by 5 plus scort.
Well, when you multiply the denominators, 5 scort 5, 5 scort 5, it's a difference of squares pattern. 52 scort 5, 2, which is 25, 5 plus 20. No more radical down there.
Nice. And the numerator.
You'll have to FOL scort 5 plus scort 2. That gives you 5 scort 5 plus 5, 10, 2 scort I5. Combining terms, you get 3 scort 5, 5.
So the final result is 3 scort 5, 20.
Exactly. It looks cleaner and is often easier for the next step and a bigger calculation.
Okay, let's shift gears. We're taking a journey now beyond real numbers into complex numbers and functions.
Right, complex numbers. These combine a real part and an imaginary part using I, where I is the square root of -1. They let us solve things real numbers can't.
And doing operations like A, B, C, where A with Jan is 3 plus 5i, B is a 4, 2i, and C is 1 plus 6i. How does that work?
You just follow the order of operations, but you treat I carefully, remembering I2 equals -1. First, multiply B and C, so 4, 2i, 1 plus 6i. You FOI all that out.
Okay, 41 is 4, 46i is 24i, 9s2i1 is 2i, and 9s2i6i is nadical 12i2.
Good. And since I2 is nadical 1, that nadical 12i2 becomes plus 12.
Ah, right. So BC is 4 plus 24i, 2i plus 12. Combining terms gives 16 plus 22i.
Perfect. Now we need ABC. That's nadical 3 plus 5i. 16 plus 22i.
And combine real parts and imaginary parts separately. Negative 3, 16 is negative 19. 5i, 22i is negative 17i.
So the result is negative 19, 17i. And the packet mentioned this lands in quadrant 3.
Right, because both the real part, negative 19, and the imaginary part, negative 17, are negative. It shows how operations position these numbers on the complex plane.
And speaking of I, its powers are cyclical, right? I gives a 1, I3i, I4, 1. This cycle of 4 is incredibly useful.
Why so useful?
Because it's a massive shortcut. If you need to simplify something like x3, I6 plus 2 by a 12,
okay,
you don't need to calculate I6 the long way. You just figure out where it falls in the cycle. 6 divided by 4 has a remainder of 2. So I6 is the same as I2, which is negative 1.
Ah, okay. And I12, 12 divided by 4 has a remainder of 0.
The remainder of 0 corresponds to I4, which is 1.
So the expression becomes by 3 to 1 plus 2 by 1.
Yep, which is negative 3x plus 2x.
Just nadig x, huh? The packet says nadig just 25x. Let me recheck the example. x3i6 plus 2 by 12. Ah, wait. The packet result shown was for a different problem involving I, maybe something like 5xi6, 10xi12, leading to 5x managed 1, 10 by 1. That's 15x. Let's look at the problem described. x3i6 plus 2 by 12. Our calculation mat6 seems correct based on the cycle. Let's assume the packet reference nagish 25x was for a different example entirely. Again, the method is key.
The method is definitely key. Understanding the cycle saves a ton of work.
And then multiplying and combining complex expressions like 2xi, 2 by 1, 2x plus 3i. Looks like more careful algebra.
It is. You need to if-while the first part. 2xi, 2 by 1 gives 4 by 2 by 2 by 2x plus I.
Okay.
And you subtract the 2x plus 3i, so 2 by 3i.
Okay, so altogether, 4 by 2 by 2xi plus I, 2 by 3i.
Now combine like terms. Real parts, 4 by 2 by 2x is 4 by 2, 4x. Imaginary parts. Netted to 2x plus I, 3i. That's I, 2x plus 1, 3, which is I, 2 by 2. Or 2x plus 2i.
Wait, the packet simplification for this one was managed for 4, 8i. Let me check my FOIL again. 2xi, 2 by 1 first. 4 by 2 outer, nanish 2x inner, nanish urli last plus I. Okay, then subtract 2x plus 3i. So 4 by 2 by 2y cos plus I, 2 by 3i. Combining reals, 4 by 2, 4x. Combining imaginaries, I data 2x plus 1, 3 equals I data 2 by 2. So the simplified form is 4 by 2, 4x plus I, 2 by 2. This doesn't match metaphor 8li. There might be typos in the source material references provided in the outline. Let's assume the type of problem is correct, even if the specific number of results cited might be off. The process involves FOIling, handling I, and combining real and imaginary parts to get the A plus by form.
Exactly. It's a good workout for those algebraic skills, making sure you separate the real and imaginary components.
So connecting this to functions, let's revisit the basic idea. What makes something a function?
It really boils down to predictability. For every input, there's exactly one output. That's the rule.
And the vertical line test.
That's the quick graphical check. If you can draw any vertical line that hits the graph more than once, it fails the test. It means one input, x value, corresponds to multiple outputs, y values. So not a function. Functions give us that consistent relationship.
Okay. And inverse functions, they sort of undo the original function?
They do, precisely. And finding them is pretty systematic. You take your function, say hx, x4, x plus 5. First, you replace hx with y. So y, x4, x plus 5.
Then swap x and y.
Yep, xy plus 5. Now, the hard part. Solve this equation for y.
Okay, multiply both sides by y plus 5 to get xy plus 5 equals y4. Distribute y plus 5x equals y4.
Good. Now get all the y terms on one side and everything else on the other. So x, y, y, go y by 1, make us 5 by 4.
Almost there. Divide by x, y made us 5 by 4 by 1. Or you could write it as yx plus 4, 1x by multiplying top and bottom by middle 1.
And that's the inverse function, hs1x.
That's it. It literally reverses the mapping of the original function. Then we have composite functions, putting one function inside another. If fx equals 3 by 2 plus 2 by 1 and gx equals 2 by 1, what's going on with fgx plus gx?
It's like layers of operations. First, you figure out fgx. That means you plug gx, which is 2 by 1, into the function f everywhere you see an x.
So fgx equals 3, 2 by 1, 2, plus 2 by 1, 1.
Exactly. You need to expand 2 by 1, 2, distribute, and combine terms there.
Okay, that's the first part. Then the second part is fx plus gx.
Right, just add the two original functions, 3 by 2 plus 2 by 1 plus 2 by 1. That simplifies to 3 by 2 plus 4 by 2.
And finally, subtract the second part from the first part.
Yep. You take the fully expanded and simplified version of fgx and subtract 3 by 2 plus 4 by 2. The packet calculation leads to 9 by 2, 12x plus 2. It shows how you can combine functions in complex ways.
And a really practical application of functions is the average rate of change. How does that help us understand things?
It's basically about finding the overall trend over an interval, like finding the slope between 2 points on a curve. So if you're tracking, say, a credit card balance, the average rate of change tells you how much it increased or decreased per month on average between two specific dates. Or, for world population, calculating it between 1950 and 1960 gives you the average number of people added per year during that decade.
The packet said about 48.78 million people per year then.
Right. It gives you a single number that summarizes the change over that time period. Very useful for spotting trends.
Okay, let's move into decoding graphs and equations, especially linear, quadratic, and polynomial functions.
Solving systems of linear equations is, well, fundamental, especially when you have three variables. Like the system x plus 2yz equals 3, 2x plus y plus z equals 5, and x plus y plus z 4.
3 equations, 3 unknowns.
The goal is to find the one point, x, y, z, that makes all 3 equations true at the same time. You can use methods like substitution or elimination combining equations to get rid of variables one by one.
And for this system, the solution turns out to be -2, 3, 1.
Correct. It's the unique intersection point of those 3 planes in 3D space.
And things get visually interesting when we find intersections of different types of functions, like a circle and a line. How do we find where x to self 1, 2 plus y to 2, 4 and y equals 2 by 2 meet?
Algebraically, it's about substitution. You know y in terms of x from the line equation.
So plug 2 by 2 inst for y in the circle equation.
Exactly. You get x12 plus 2 by 2, 2 equals 4, which simplifies to x12 plus 2 by 4, 2 equals 4.
Now you have an equation with only x. You have to expand those squares.
Yep. Expand combined terms, and you'll end up with a quadratic equation in x. Solving that quadratic gives you the x-coordinates of the intersection points.
Then plug those x values back into the line equation y, or 2 by 2, to find the corresponding y coordinates.
That's the process. For this specific pair, the intersection points were 215, 325, and 1 Farova. It shows where the line crosses the circle.
Very cool. And what about going the other way, starting with data points and finding an equation?
That's where statistical regression comes in. If you have a set of ordered pairs, regression techniques can find the best fit polynomial equation for that data.
Like the example where data led to a cubic equation, y equals by 3, 2x plus 2.
Exactly. This is huge in science and engineering, taking experimental data and creating a mathematical model from it.
And transforming graphs, it's like manipulating the functions pictured directly.
Yeah.
How do changes in the algebra affect the graph?
But it translates very predictably. If you have fx and you change it to fx2, 3,
Oh, yeah?
the x2 part means shift the graph 2 units to the right. The -3 outside means shift it 3 units down.
And something like f2x.
The 2x inside means a horizontal compression squishing it towards the y-axis by a factor of 1/2. The negative sign outside means reflect the whole thing across the x-axis.
Understanding these rules means you can visualize the transformed graph without plotting lots of points.
It's a very efficient way to understand function behavior.
Now let's dig into polynomial behavior a bit more. Sketching them from their roots seems useful.
It really is. The roots, or x-intercepts, tell you where the graph hits the x-axis, but the multiplicity of the root tells you how it hits the axis.
Multiplicity.
Yeah, how many times that factor appears. If a root has multiplicity 2, like from a factor x3, 2, the graph touches the x-axis at x3 and bounces off.
Okay. Doesn't cross.
Right. But if a root has multiplicity 1, like from a factor x1, the graph crosses the x-axis at x1. Odd multiplicities cross, even multiplicities touch and turn back.
That gives you a basic shape between the roots.
It gives you a really good starting point for the sketch.
There was that interesting example in the packet, though. A graph shown had intercepts at -2, 1, and 3. But the equation given was y x1 by 2, 5 by 6.
Yes, that's a great cautionary tale. If you factor the quadratic part by 2, 5 by 6, what do you get?
Factors of -6 that add to -5. That's x6, x plus 1.
Exactly. So the full equation is y x1, x6, x plus 1. What are the roots of this equation?
1, 6, and -1.
Not -2, 1, and 3, like the graph showed.
Wow, so the graph and the equation didn't match.
They didn't. It's a really important reminder to always verify. Factor completely, check the roots, make sure everything aligns. Don't just assume.
That's a really good point. Precision matters. And how does the degree of the polynomial relate to its roots?
The degree of the highest power of x tells you the total number of roots the polynomial has. This includes real roots and complex imaginary roots.
So a 4th degree polynomial always has 4 roots.
Always 4 roots, counting multiplicity. Some might be real, some might be complex. If it has, say, 2 real roots and 2 complex roots, how many times will its graph cross the x-axis?
Only twice, because only real roots are x-intercepts.
Precisely. The degree gives the total, but the graph only shows the real ones.
And we can also go backwards, build a polynomial if we know its intercepts and maybe one other point.
Yes. If you know the x-intercepts, say counting 4, -2, 1, 3, 5, you can start writing the polynomial in factored form. Y, c, x plus 4, x plus 2, back 1, back 3 by 5.
Where c is some constant multiplier.
Right. Then if you know another point it passes through, like the y-intercept 0, -4, you plug in x equals -4 into that equation.
So -4, c, 0 plus 4, 0 plus 2, 0, 3, 0, 5.
Calculate that product as numbers. 4, 2, 3, 1, 3, 3 through 5 is 8, 15. No, 8 through 1 through 3 through 3. 815 equals 120, but negative. So negative 120.
Negative 120.
So c equals 4 negatives of 120, which simplifies to 130. Now you have the specific polynomial equation.
It's like designing the function from its key features.
Exactly.
Okay, let's dive into quadratic equations specifically. Parabolas, how do we get their equation?
You usually need key information like the vertex and the direction it opens,
Right.
or maybe the focus and directrix, for instance, a parabola with its vertex at 3, 2, that opens upwards. Its equation will be in the form xh2 equals 4pyk.
Where x is the vertex, so x32 4p y ns 2, or x32 equals 4p y plus 2.
Right. The 4p value determines how wide or narrow it is. The packet example suggested x32 equals 12y plus 2, which implies 4p12, so p3.
And these parabolic shapes show up in the real world, right? Like projectile motion.
Oh, absolutely. It's a classic application. An equation like ht e equals 6t2 plus 184t can model the height out of a rocket in feet after 2 seconds. The negative 16t2 part comes from gravity.
So if we want to know when the rocket reaches, say, 522 feet,
You said ht equal to 522, so 522 equivalently 16t2 plus 184t. That's a quadratic equation you need to solve for t.
rearrange it. 16t2, 184t plus 522 equals 0. You'd probably use the quadratic formula here.
Probably. And when you solve it, you often get 2 positive answers for t.
Why 2?
Because the rocket passes that height once on the way up and again on the way down. The packet showed the times were 5.1 and 6.4 seconds.
Makes sense. But quadratic equations don't always give real number answers, do they?
No, sometimes the solutions are complex numbers. Take by 2 of 4 by 8. If you rearrange that to by 2, 4x plus 8 equals, and try the quadratic formula.
The part under the square root, the discriminant b248c, would be negative of 4x248. That's 1632 equals 16.
Exactly. You get the square root of negative 16.
Okay.
Since it's a negative, there are no real solutions. The parabola y equals by 2 4x plus 8 never touches the x-axis.
But there are complex solutions. Square root of negative 16 is 4i.
Right. So the solutions for the quadratic formula are x forming only as is 4i2, which simplifies to x to more than as of 2i. It's a reminder that solutions can exist beyond the real number line.
And finally, for quadratics, completing the square, that seems like a really versatile technique.
It is. It's got 2 main uses. First, you can use it to solve quadratic equations like 2 by 2 plus 24x equals 64.
How would that work? Divide by 2 first. By 2 plus 12x equals 32.
Good start. Now take half of the coefficients of x, which is 12, half is 6, and square it in 36. Add that 36 to both sides.
By 2 plus 12x plus 36 equals 32 plus 36.
The left side is now a perfect square, x plus 6, 2. The right side is 4, so x plus 6, 2 equals 4.
Take the square root of both sides, x plus 6 plus 2, which is minus 4, or x and add to 6, 2, which is 9, which is 8. Same answers you'd get from factoring or the quadratic formula.
Okay, so that's one use. What's the other?
The other big use is transforming equations of conic sections, circles, ellipses, hyperbolas into their standard forms. This reveals key information like the center and radius of a circle.
Like the example 3 by 2, 18x plus 3y2 plus 54y equals 57.
Yeah, you group the x terms and y terms, factor out the leading coefficients, and complete the square for both x and y.
So 3 by 2, 6x plus 3y2 plus 18y equals 57. Complete the square inside the parentheses. For by 2, 6x, half of negative 6 is 9 is 3, squared is 9. Add 9 inside. For y2 plus 18y, half of 18 is 9, squared is 81. Add 81 inside.
3 by 2, 6x plus 9 plus 3y2 plus 18y plus 81 equals 57 plus 8.
Wait, what do we add to the right side?
Careful. You added 9 inside parentheses that are multiplied by 3, so you really added 39 equals 27 to the left side.
Okay. And for y, we added 81 inside parentheses multiplied by 3, so we added 381 equals 243.
Right, so the right side becomes 57 plus 27 plus 243, which is 327.
And the left side becomes 3 by 3, 2 plus 3 plus 9, 2 plus 9, 2 plus 9, 2.
Perfect. Now you can see it's a circle centered at 3, 9. You could divide by 3 to get the radius squared. It reveals the geometry.
That's really powerful. Okay, next up, the exponential and logarithmic worlds. Growth, decay, finance.
Exponential functions are just incredible for modeling things that grow or shrink at a rate proportional to their current size. Classic examples are population growth or radioactive decay.
Or money. Compound interest.
Definitely compound interest. The packet had an example of a blackbird population. BT equals 750, 1.16 T12.
What does that mean? 750 is the starting population. Yep. T in Ds, time may be months. The 1.1 12 shows a growth factor. It's equivalent to rewriting it as BT, 750, 1.1 speeds. You calculate 1.1 seat for 112, it's about 1.012.
So BT equals 750 1.012T. That looks like about 1.2% growth per month.
Exactly. It shows that monthly compounding growth factor.
And logarithms are the inverses of exponentials, right? They have their own rules.
They do, and those properties are super useful for manipulating equations. You can condense multiple logs into one or expand one log into many.
Like condensing 2 log x, 13 log y.
The 2 in front becomes an exponent on the x, so log x2. The 13 becomes an exponent on the y, so log y13 or log cubic.
Okay, so log x2, log cubic. And subtraction of logs corresponds to division inside the log.
Right, so it condenses to log by 2 cubic y.
And expanding log, AB2.
Multiplication inside becomes addition outside, log A plus log B. Division inside becomes subtraction outside, log C2, and the exponent comes down, 2 log C.
So log A plus log B, 2 log C.
Yep. These rules let you rearrange logarithmic expressions effectively.
Which helps in solving equations involving them. What's the general strategy?
If you have an exponential equation like 87e.3x equals 5918, first isolate the exponential term, divide by 87.
E.3x equals 591887, which is about 68.02.
Now take the natural logarithm, ln, of both sides to undo the e. So ln e 0.3x equals ln 68.02.
The left side is just 0.3x.
Right, so 0.3x was ln 68.02. Calculate the natural log, then divide by 0.3 to find x. The packet got x goes 14.066.
And for logarithmic equations, like log x plus 3, 2x plus 3, x plus 5 equals 2, assuming x plus 3 is the base.
Okay, if x plus 3 is the base, the sum of logs with the same base means you multiply their arguments.
So log x plus 3, 2x plus 3, x plus 5.
X plus 3, 2 equals 2x plus 3, x plus 5. Now it's an algebraic equation. Expand both sides.
By 2 plus 6x plus 9 on the left, 2 by 2 plus 10x plus 3x plus 5, or 2 by 2 plus 3x plus 15, or 2 by 2 plus 13x plus 15 on the right.
Move everything to one side. 0 yields by 2 plus 7x plus 6. That factors nicely. X plus 1, x plus 6 equals 0, 0. So potential solutions are x1 and x6.
But wait, we have to check for extraneous solutions, right? Especially with logs. The base, x plus 3, cannot be negative or 1. And the arguments 2x plus 3 and x plus 5 must be positive.
Crucial check. If x is minus 6, the base is minus 6 plus 3 equals 3. Can't have a negative base, so x6 is extraneous.
What about x minus 1? The base is minus 1 plus 3 is 2. That's okay. The arguments are 2 to 1 plus 3 equals 1 and minus 1 plus 5 equals 4. Both positive.
So x1 is the only valid solution. You must check those domain restrictions for logs.
Good point. Now for real-world stuff, visualizing these graphs helps, like y Oriel 2 by 3 plus 1.
Right. Compared to the basic y log 2x graph, the x3 shifts at 3 units to the right.
Meaning the vertical asymptote moves from x0 to pi3.
Exactly. And the plus 1 shifts the whole graph up 1 unit. Understanding these transformations helps interpret models of growth or decay visually.
And compound interest feels like a really powerful real-world example.
Oh, it's huge. It drives so much of finance. We can use logs to figure out how long investments take to grow. For example, how long to double money at 3.75% compounded continuously.
Continuous compounding uses the formula A equals PERT. We want A to be 2p, so 2p equals p 0.0375t.
Divide by p2 equals e 0.0375t. Now take the natural log of both sides.
ln2 equals ln 0.0375t. So ln2 equals ln2.0375t. So ln2.0375, calculate that, and it's about 18.5 years.
It's handy. And we can compare different scenarios, like Jose investing $200 at 10% compounded quarterly versus Marion investing $150 at 14% compounded continuously.
Yeah, you just use the appropriate compound interest formulas for each. For Jose, quarterly, it's A equal P1 plus Rn. For Marion, continuously, it's A equal T. Plug in the numbers for T5 years.
The packet showed Jose ends up with $327.72 and Marion with $302.06. So Jose did better over 5 years, even with a lower rate, because he started with more money.
Right. But you could also use logs to figure out when their investments would be equal. Set their formulas equal and solve for T. It turns out it's around 7.0 years. So Marion's higher rate would eventually overtake Jose's investment.
Shows the power of interest rates over the long term.
And mortgages, too. That formula looks complex.
It does, but it's derived from these same principles of present value of an annuity. For a $237,000 loan at 4.5% over 20 years, the formula yields that monthly payment of $1,499.38. It's a direct application.
What about decay, like medication half-life?
Same idea, but with a base less than 1. A model like AT, 312T6.5, represents 300 milligrams of a drug with a half-life of 6.5 hours.
So 12 is the decay factor, and T6.5 tells you how many half-lives have passed.
Exactly. You can use this to calculate how much is left after a certain time or how long it takes to reach a certain level. Like finding T when AT is 55% of the original 300 milligrams.
55% of 300 is 165. So 165 is equivalent to 12, T 6.5. Solve for T.
Yep. Divide by 300, take logs of both sides, either natural log or log base 10 works, and solve for T. The result was about 5.6 hours, vital for dosing schedules.
And Newton's law of cooling. That turkey example was interesting.
It's another exponential decay model, but it decays towards the surrounding temperature, not towards zero. The formula involves the temperature difference.
So the turkey cooling from 350 degrees air towards the room temp of 68 degrees air.
Right. Using the temperatures at different times allows you to find the cooling constant K. The packet found K equals 0.082. Once you have K, you can predict the temperature at any other time.
Like predicting it would be 178 degrees air at 4 p.m.
Exactly. It's used in forensics, food safety, all sorts of fields.
Okay, last section. Rational expressions and more advanced equation solving.
Rational equations, those fractions with variables in the denominator, require that extra careful step, checking for extraneous solutions.
Why again?
Because the solution you find algebraically might make one of the original denominators 0, which is undefined. You have to discard those.
Like in 212 3x as 4x by 3. Notice 3x and x3 are opposites.
Good catch. You could rewrite 12 3x as net is still 12 by 3. So the equation becomes 2 plus 12 by 3 equals 4x by 3.
Multiply everything by x3 to clear the denominators, assuming x is not 3.
Yes,
Yay.
you get 2 by 3 plus 12 by 3 plus 12, 4x.
2 by 6 plus 12 equals 4x. So 2x plus 6 plus 6, 4x.
Subtract 2x, 6 was 2x, which means x was 3.
But wait, we assumed x was not 3 to multiply by x3.
Exactly. Our only potential solution, x3, is the one value that makes the original denominator 0. So it's extraneous.
Meaning there's no solution to this equation?
Correct. No solution. Always check.
And simplifying complex rational expressions, that looked like a factoring marathon.
It often is, like simplifying x22 by 2 by 6, x3 by 2, 4.
You have to factor everything first. By 2 by 6 is x3, x plus 2, and by 2, 4 is x2, x plus 2.
Right. Substitute those back in. x22 by 3, x plus 2, x3, x2, x2, x22.
Now cancel common factors. 1 x2 cancels, the x3 cancels, the x plus 2 cancels.
So that's left. Just one x2 from the x2 upstairs.
So-
Wait,
so-
the packet simplification said x plus 2. Let me recheck the expression. x2 by 2 by 6, x3 by 2, 4. Factors. Numerator x2, x2 by 3, x plus 2. Denominator x3, x2, x plus 2. Canceling x3, 1, x2 leaves just x2. Another potential typo in the cited solution. The process gives x2. Let's trust the process.
Okay, trusting the process. What about radical equations like 3 squared tx, 2x gas, Varana 5? Checking is crucial here too.
Absolutely. Because the main way to solve this is to isolate the radical 3 squared tx equals 2 by 5 and then square both sides.
Square on both sides. 3 squared tx, 2 equals 2 by 5, 2. That's 9x, 4 by 2, 20x plus 25.
It becomes a quadratic equation. 4 by 2, 29x plus 25 equals 0. You solve this quadratic maybe by factoring or the formula. The packet indicates the solutions to this quadratic are x1 and x of 254.
Now check them in the original equation. 3 squared tx, 2x, that's 5.
Try x1. 3 squared t1, 3, 2, 2, after 1 minus 5 is 5. So x1 is extraneous.
3x, 2, 5, 2, 4, 244, 2294. That's 352, 504, which is 152, 255.
Right. Does 5 equals 1 and 5? Yes. So x254 is the valid solution.
Squaring both sides can introduce those false solutions.
It often does. You have to check.
And equations with rational exponents, like by 432, 5 equals 20.
Isolate the term with the rational exponent first. Add 5 to both sides by 4, 32, and 25.
Now how to get rid of the 32 power?
Raise both sides to the reciprocal power, which is 23. So by 4, 32, 23, 25, 23.
The left side simplifies nicely to just by 4.
Right, so by 4 equals 25, 23. That means the cube root of 252 or the cube root of 625.
So 25 isn't a perfect cube. Let me recheck the packet note. It said x plus plus net 500. Where does that come from? Let's retrace. By 4, 32, 25, raised to 23 power, by 4 equals 25, 23. 25, 23 is 52, 23, so x 4, 5, 43. That's not 500. What if the equation was by 4, 23, 5 leaves 20? Then by 4, 23, 25. Raise both sides to 32. By 4 was 25, 32. 25, 32 is square root to 25. So by 4 and 25 and x equal 500. That matches one part. Where does the plus might come from? Usually when taking an even root, Curie raised to the 32 power, which involves the square root. When we solve y2k, y plus negative square k, and we solve y23 at 23, that's y13, 225. So y13 plus negative 1 makes 5, then y plus negative 5, 3. So y plus 125, or y is 125.
Right.
Applying this logic to by 4, 23, 25, we get by 4 plus negative 25, which means x plus less negative 500. It seems likely the original problem intended was by 4, 23, 5 equals 20.
That seems plausible given the answer. The key is using that reciprocal power to isolate the variable.
Finally, translating word problems into equations. These can be tricky, like work problems. Mary takes 16 minutes longer than Antoine. Together, they take 6 minutes.
The key is to think about their rates of work, how much of the job they do per minute. If Antoine takes X minutes, his rate is 1x jobs per minute.
Mary takes X plus 16 minutes, so her rate is 1X plus 16 jobs per minute.
When they work together, their rates add up. Their combined rate is 1x plus 1x plus 16. Since together they take 6 minutes, their combined rate must also equal 16 jobs per minute.
So the equation is 1X plus 1X plus 16 equals 16.
Exactly. Now you have a rational equation to solve for x.
And distance, rate, time problems. Passenger train 27 mph faster than freight train, same travel time, different distances, 375 miles versus 260 miles.
The key here is that the time is the same for both. End time equals distance rate.
Let the freight train speed be X, then the passenger train speed is X plus 27.
So the freight train's time is 260x. The passenger train's time is 375x plus 27.
Since the times are equal, we set them equal. 260X equals 375X plus 27.
And there's your equation. Again, it's about translating the relationships in the story into algebraic terms.
Phew. So we've really journeyed through quite a range of math today, from basic polynomial operations all the way to logarithms, complex numbers, and applying it all.
It's quite a spectrum. But what really stands out, I think, is how interconnected it all is.
Yeah.
Definitely. Mastering factoring helps with rational expressions. Understanding exponents is crucial for logs. Function concepts apply everywhere. It's not just isolated topics, it's a whole logical system.
It builds on itself.
Exactly. And mastering one part really does unlock the next. It shows the elegance and efficiency of thinking mathematically.
So as you, our listeners, reflect on this deep dive, maybe consider this. How does getting comfortable with these tools, the factoring, the exponent rules, solving equations, understanding functions, how does that not just help with math tests?
Right. How does it sharpen your ability maybe to break down any complex problem, to see the structure underneath, to interpret quantitative information you encounter every day?
These aren't just abstract numbers and symbols. They're lenses, right? Tools for understanding, modeling, and just interacting with the world in a more informed way.
Well said. They
Yeah.
really are powerful lenses.
Yeah.